Hello students, in this session we will discuss about threaded binary tree and one more concept, priority queue. First one, threaded binary tree. Now you are all familiar with binary tree concept. So in binary tree concept, in linked representation, if a child node is not available, then their left child, right child, those not available, then those are filled with null pointers. So in threaded binary tree concept, it is a special type of binary tree representation in which those linked parts where the null pointer is available, those are also filled with address of some specified nodes, and these special links are known as threaded links. Such a binary tree is treated as threaded binary tree. Now observe this one. So threaded binary tree is a binary tree in which the null subtree links, that means those are null pointers, are filled with thread links. So thread link is a pointer that points to other nodes of the binary tree. See how it should be. Now here, if right child of node is null, then the null pointer is replaced by a thread which points to the node that occurs after the node when the binary tree is traversed in order. If L child of a node is null, then the null pointer is replaced by a thread which points to the node immediately precedes node when the binary tree is traversed in order. So to design thread links, first identify the in-order traversal of the binary tree. Then, based on the node childs, if for the node right child node is null, then in binary order, whatever the node that is available after the specified node, so null pointer is replaced with that particular thread. If L child of node is null, then predecessor node link is pointed to null pointer. Okay. Now observe this example. It's a binary tree. This one linked representation of a binary tree. So here number of null pointers are available. Now these null pointers are replaced with thread links. Now observe this format. Now here, first we design in-order traversal of the given binary tree. Now it shows in-order traversal G, F, B, A, D, C, E. Now, to design threaded binary format, here the procedure starts by indicating a header node. So this header node stores address of the starting node. So here the address of the starting node is A. Now from A, left child is B, right child C. For B, left child, for A, left child B. So for B, left child is F. Here the right child is a null pointer. Hence here right child is null pointer. So in in-order traversal, for B, rightmost node is A. Hence, now this link points to node A. For C, left child D, right child E. Coming to F, left child is G. Now right child is a null pointer. So F point of view, right node is B. Hence, this link pointer points to node B. For D, here the left child is A, hence it points to A. Now right child is C, then it points to C. For E, left child is C, hence it points to C. Now, for F, left child is G and its right child. For G, F is the right node, hence it points to F. Now, for G, left node is not available, hence here we place a link that points to header node. For E, right child is not available, so its right line points to header node. So these two links are known as dangling thread links. The remaining links are treated as thread links. Okay? Now, such a representation is known as threaded binary tree. Okay? Next concept, priority queues. Now listen, a priority queue is a collection of 0 or more elements in which each and every element has a priority. So to implement the specific operations like insertions and deletions, it must follows the priority rules. Now you are all familiar with priority rules. So highest priority element is processed first before the lowest priority element. If two or more elements have same priority, then they follows the order in which they are entered for processing. So these are the priority rules. Now here, the basic operations on a priority queue are insertion, deletion, display operations. Now, based on the priorities concept, the priority queue can be classified into two types, like min priority queue and max priority queue. So in min priority queue, minimum priority element is processed first before the maximum priority element. In max priority queue, first maximum priority element is processed, then low priority element. So this one, in main priority queue, minimum priority element is processed before the maximum priority elements. In max priority queue, maximum priority elements are processed before the minimum priority elements. Now, to implement these operations, here one important concept is there, heap tree. Now listen, suppose H is a complete binary tree. Now, the tree is treated as heap tree, is also referred as max heap. It's an important point, max heap. If it is satisfies the properties like for each node n in H, the value at n is greater than or equal to the value of each of the children of n. So parent value is greater than the child value. This is a basic principle of max heap. Now observe this example. So 95, 84, 48, 76, 23. Now when we observe this format, at any stage, parent value is greater than or equal to child value. So 95 is greater than 84 and 48. 84 is greater than 76 and 23. Such a representation is known as heap tree, which is also referred as max heap. Now, representations of a heap tree. So heap tree is a complete binary tree, hence it is better to represent in terms of a single dimensional array, so that it saves lot of memory space. Now observe this example. So for this heap tree, the array representation is 95 stored in index 1, 85 in index 2, 48 in index 3, 76 in index 4, 23 in index 5. It shows array representation of a heap tree. Now coming to the basic operations on a heap tree, so are similar to other representations and operations. Here also insertion, deletion, display, merging, all are basic operations that can be applied on a heap tree. Now first operation, insertion into a heap tree. Now assume K is an array which stores n elements of a heap tree. If a new information is available in K for insertion operation, the basic steps are: first, add the element at the end of the K, so that still tree is a complete binary tree, but it may not be necessary to form as a heap. In such cases, we write the key values into appropriate position in the same path, so that finally it becomes a heap tree. So by applying these two basic principles, we can simply insert the element into a heap tree. The same way, deletion operation. So here this operation is used to delete an element from the existing heap tree. For this, the basic procedure is: first, assign the root node value into a temporary variable as key. Then replace the root node by the last element of the heap tree. Then tree is a complete binary tree, but sometimes it may not be satisfies the properties of heap tree. In such cases, we readjust the elements, like assume the newly modified root node as the current node. Now compare the current node value with its two children nodes. Assume in those children nodes, if x is the highest value, then interchange x with the current node. Then next stage, make x value as the current node. Apply the same process until the current node is not an empty node. Whenever process reaches to null pointer, then we terminate from the procedure, so that finally the tree satisfies max heap properties. Okay, thank you one and all.